these are the notes for section 2.4. And the definition of continuous function is a function f is continuous at a number a if the limit as x approaches a of the function equals the actual value at a. So it's kind of like it sounds, the function would be continuous, like there's not a hole in the graph or a break in the graph or anything like that. So let's look at a couple examples at the bottom. And it says, explain why the following three functions are not continuous at x equals 2. So here we see there's a hole in the graph, and going by the formula, we can see that the function is not equal to f of 2. F of 2 of this function is undefined. Here, the actual value at f of 2 is this dot, but the limit is approaching here. And then same with this, we see kind of a break in the graph. So here the limit is undefined. Here they're just not equal, and here the value at f of 2 would be undefined. So if you want to just kind of pause that and study those over and write those three situations down. All right, a function is continuous from the right of a number a if, so the limit as it approaches a from the right is equal to whatever value you're looking at. And then the kind of opposite is true if a function is continuous from the left of a number a if the limit as x approaches a from the left is equal to that value. And then if you want to just kind of make note of this, a function's continuous on an interval if it's continuous for every number on that interval. Okay, pay attention to the limit laws in your book. So what we're trying to show here is that this function is continuous on the interval -1 to 1 with closed dots. So if we have a is anywhere between -1 and 1, I'll probably do that, then using limit laws we have this. Okay, all I did here is I'm just kind of writing that continuous function, and I just kind of rewrote the function here. Now, looking at the laws, since this is just a number, that's just a constant, we're allowed to write that out front and then just talk about what happens as the limit approaches a. And then looking at law 11, if we're dealing with a square root, we're allowed to input this limit inside here. And now we could plug in the a and see what happens is as x approaches a, this will just become 1 minus a squared. And that is equal to f of a. Like if you would just plug a into this function, it would be 1 minus radical 1 minus a squared. So you're just trying to use that limit laws and rewrite it to kind of show that it is continuous. Okay, if you just want to pay attention to these theorems and read them over. In Theorem 5, we'll use a lot. Every polynomial is continuous over all real numbers, and every rational function is continuous over its domain. That really makes it simple if you see you know, here we have a rational function and a polynomial function. And fix this, please, to say x cubed plus 2x squared minus 1. If you guys could kind of update that. So we know it's a rational function. So by Theorem 5, Part 2, it's continuous over its domain. But then we want to remember its domain, this is not allowed to equal 0. So if 5 minus 3x is not allowed to equal 0, if we just solve this, so I'm just going to move my 5 over here, then divide by -3. X is allowed to equal anything except for 5/3. So that is its domain. That's how you kind of word that. And then to find the actual limit as x approaches -2, we can, what we can do is just plug in -2 and it works. It ends up being -1/11. okay, if you want to read over, this is theorem 8, if you want to label that. And again, all these theorems are in your book. If f is continuous at b and the limit as x approaches a of g of x equals b, then you know the limit as x approaches of a of f times g of x is going to be the value f of b. I know that looks like a lot. So in other words, maybe kind of look at this to help us out. Good news is we're going to do this homework together. So if you guys just kind of keep doing the best you can to take notes and understand them as best you can, we'll work on the book problems together. All right, so we're going to use this theorem to find the limit of the inverse sine as x approaches 1 of this function. Okay, so what I did was, you can kind of think of sine being its own term and writing that out in front by this kind of theorem that we just talked about, like this f can be written out front. Limit as x approaches 1 over radical x over 1 minus x. Now the problem with this is we can't plug a 1 in to this formula. So what I've shown up here, ooh, that's pretty smart. Okay, there maybe was a better way to do this, but I kind of crossed it out. But what I did on the bottom here is I did 1 minus radical x and 1 plus radical x. What would you do if we FOIL that? So the first term would be just 1. The outer and the inner terms are going to cancel, and then we're going to have negative x. So this can actually be factored so that we can cancel the numerator and denominator, leaving us with 1 over 1 plus radical x. Now we can plug the 1 into this, and it becomes 1 over 2. And now inverse sine of half, well, I drew a 30, 60, 90 triangle. And then a 30 degrees is a 1, 2, radical 3. So sine of 30 degrees leads you to 1/2. And 30 degrees, remember, is equal to pi over 6. So pi over 6 is the solution to that limit. All right, we're almost done. So this is a theorem. If g is continuous at a and f is continuous at g of a, then remember how we learned about composite functions? F of g is continuous at a. So we can apply that. And here, like if you're like, well, I don't know what sine of x squared looks like, that's okay. Let's kind of break this into two functions, and I'm going to call them f of x and g of x. So, and like this being a combination of all of them. So if I think of g of x as just being x squared, okay, and then f of x of being sine of x, if I like put them together, like I, plugged this x into x squared, see how we get back to where we started? Like I made a composite function like this. Well, if you know each of these are continuous, so we know x squared, you guys know that's a parabola, is continuous. It's just a polynomial, and we know all polynomials are continuous. We know sine of x is just constant like this, is continuous everywhere. So by theorem 9, the composite of those two would also be continuous on all real numbers. So if you just know what each graph is continuous, you know this graph is continuous, there's no break in the graph. We know this graph is continuous, there's no break in the graph. So the composite of both of them together would also be continuous. Okay, and then B kind of did the same thing. I thought of this as a composite function, natural log of 1 plus cosine x. So if you think of what the natural log function looks like, it's the inverse of an exponential function. I don't think kind of looks like that. And then 1 plus cosine x would be the cosine function, just up 1. Since they're both continuous, by theorem 9, the whole composite is also continuous. And finally, the intermediate value theorem. You guys can read that from the book, or you can read it here, but I do want you to study the graphs on page 126. This seems complicated, but it really isn't when you do a problem. I kind of like this better than the past few example problems we've had. So suppose f is continuous on this closed interval, so it has to have the closed brackets a and b. Let n be any number between f of a and f of b. So, you know, if we had this being like 0 to 5, you could pick like anything between there, like f of, 0 and f of 5. and you don't want them to be equal to each other, there's going to exist a number c in this interval such that f of c equals n. Okay, and again, I know that's a lot of information, but write it down and kind of then have it here to help us down here. So use the intermediate value theorem, IVT for short, to show the natural log of x equals x minus radical x has a solution somewhere in the interval 2, 3. So, what did I do here? Oh, okay, I just got all this to one side. So I just moved natural log of x, I brought this minus x over, I added this plus radical x, and I set it equal to 0. All right, and I said, all right, let's let our function equal this. We're looking for a number c somewhere between 2 and 3 such that f of c equals 0. F of c equals 0. And I chose 0 because this is 0. So I'm going to take a as 2 because that's this interval number. This is your a and this is your b. B is 3 and my n is 0. And then from this theorem up here, from theorem 10, I find the value of f of 2. I find the value of f of 3, and notice intermediate, like it's kind of in between 0, my n, is in between f of 3 and f of 2. It's a number between f of 3 and f of 2. Now f of x is continuous by the IVT theorem. You do not need to do this bookwork. We're going to do some of this bookwork in class on, let's see, what day would that be? Friday, next time in class, Thursday. We'll do this in class Thursday. Okay, there we go. All right, so hopefully you did all right with that.